we're starting back the afternoon session. Our first speaker, Maxime Dupont from Rigetti.
Yeah. So hi, everyone. Well, first of all, I would like to thank NERS for putting this conference workshop together and giving me the opportunity to talk. So I'm Maxime. I work at Rigetti Computing. We are a superconducting quantum computer company based here in Berkeley. But I'm not going to talk about hardware, but quantum optimization algorithm today. And in particular, a work that was done in collaboration with people at USARA, NASA, and Purdue University. And this was supported by DARPA, as well as NERS for the classical computing time. So when I say optimization problem, those are the kind of problems I'm thinking about, and they all enter the category of combinatorial optimization problems. And in the context of quantum computing, maybe the most famous one is the maximum cut problem, because that's the most studied for developing and benchmarking and testing quantum algorithm. And basically in that one, you have a graph, so nodes, edges, and the goal is to find a bipartition of the graph such that to maximize the number of edges between the two partitions. And so a combinatorial optimization problem, basically it's an optimization problem where we optimize an objective function against discrete variables. And so those discrete variables, for example, they can take values plus minus 1. From a statistical physics or condensed matters perspective, this is just equivalent to finding the ground state of a classical Ising model, where we have our classical Ising spin taking values plus minus 1, and then you have a two-body interaction encoded in this Wij. So you have your objective function, you can represent it as a graph, where the nodes are the variables, and these edges between the nodes are like the Wij. So you have problem, graph, and a graph, it's encoded by its adjacency matrix W here. So there is no algorithm in general on classical computers that will guarantee finding the optimal solution in finite time for optimization problems for general case. And so you have a zoo of heuristics which have been developed to find solutions regardless. And although they cannot guarantee the quality of the solution, while those in practice are pretty good, usually quite fast, and they also can run quite large problems and solve those. But they're not perfect. And when we have quantum computing available, maybe the idea is that, well, they're not perfect. So maybe there is room for quantum computers to do something. And we don't know that, but that's what the research is about. And I'm highlighting here two works, one by the Luckin group at Harvard, one done by Q-Control running on IBM, where they try to solve some kind of optimization problem. And in absolute value, those works are like great, and they tackle very important questions regarding quantum optimization, and they run on like about 100 qubits. But relative to like classical solvers, those aren't so great, because 100 variable problems, classical solvers, that's very easy for them. And then those quantum solutions, they are not really competitive because they are slow. You have lots of overhead. So in practice, what we want for a quantum algorithm is something that's high-performing, fast, and that can also tackle large problems. And if we think today about like the size of the quantum computers that we have, it's like about 100 qubits. Well, classical solvers are very powerful on that many variables. And so what we want, if we want something today, it's some kind of method or strategy where we can solve problems with more variables than qubit available on the quantum computer. So here's what we propose here, quantum relax and run solver, QRR for quantum relax and run. And it may be easy to start understanding what is a relax and run solver in the classical world first. And for that, well, we start with our optimization problem and its adjacency matrix W, which encodes it. A reason why the optimization problem is difficult is because it's defined over these discrete variables, which take only values plus minus 1. If we relax that constraint and say, well, the Z variables, they can now be any real numbers, well, the problems become super easy, because your objective function is just an eigenvalue problem. And to solve it, you just need to find the leading eigenvector of your adjacency matrix W. And we know how to do that efficiently. Of course, if you do that, the solution that you get, your leading eigenvector, it's not a valid solution with respect to the original problem, because The solution that you want is made of discrete variables. And so you need an extra step here to go from something continuous to discrete again. And a very simple strategy is to just sign round the entries of your leading eigenvector. So that's the relax and round, and then you can like add some stuff on top of that. One of them is, well, maybe you can say that the entries in your leading eigenvectors, which are the closest to zero or the lowest magnitude entries, you can say, well, those are the ones for which I'm the less sure actually of the sign. And so you can try to revisit greedily those entries and flip the sign, and if it gives you a better solution, you keep it. So everything is purely classical here. That's like the idea behind classical relax and round solver. Wemans-Williamson can be expressed as a relax and round solver as well. But here's what we suggest for the quantum side. You take your problem and you run the QAOA, the very standard QAOA with P layers, and you run that just as usual, like nothing changes. Where it changes is instead of considering the bit strings you sample as candidate solution to your problem, you are going to build a correlation matrix. Two-point correlation matrix, ZICJ. When you have this matrix, what we say is, well, instead of doing a relax and round on the adjacency matrix W, do it on this correlation matrix Z instead. We don't really have time to explain why that would make any sense to do that, but we can prove some rigorous results, why it works, like in some limit, show have performance guarantee. But I guess maybe some intuition as of why it doesn't give anything totally random is that if you think very locally in your system where you have a Wij which is negative, what naively you can imagine is that while a Wij which is negative, it's going to tend to align your two spins to minimize the energy. And so when you build this correlation matrix, which is minus ZICJ, if your two spins are aligned, it means that the ZICJ will also be negative. And so Wij, ZICJ, they kind of have the same information in the end. So we have the algorithm, and now we want to solve or test it on some problems. And we're going to do that on a maximum cut problem on random 3 regular graphs. 3 regular graphs, they are graphs for which at random, each node has 3 neighbors. And well, quantum algorithms, they maybe are most promising when we deal or solve problems which are large. And a nice property of the quantum relax and round algorithm is that we can access problems much larger than qubits available. And that property is that we work with expectation values and not bit string directly. So why? How does it work? Well, the underlying quantum building block is the QAOA algorithm. When we apply the QAOA on our circuit, the QAOA with P layers, that will introduce around each of the qubits a light cone with that qubit and its P nearest neighbors. Now what we want is a correlation ZICJ. And a correlation ZICJ that will only be non-zero if the 2 light cones intersect. And we know the size, the maximum size that like these intersecting light cones can have for 3 regular graphs because they have a nice regular structure. So what does it mean in practice? Well, if we are interested in only the ZICJ, and that's these expectation values, what we can do is to run the QAOA on only the qubits that are making the intersecting light cones. And the size of those is known. About like you have a correlation matrix, right? So you have like about n square entries naively to compute. So n square sub-circuits to simulate. Now I'm adding some information on that, which is like in these 3 regular graphs, the average distance between 2 nodes, it's like grows as log n, where n is the number of vertices in the graph. So that's a topological property of the graph. And when we plug all of that together, what does that mean? Well, it means that when P, the number of QAOA layers, is much smaller than log n, you don't have n square entries which are non-zero in your correlation matrix. You have actually order n, which are non-zero. So now, putting all of that together, what it means is we are trading an n qubit QAOA circuit for order n subcircuits, each with order 2 to the p qubits, when p is much smaller than log n. But on NISQ devices, which are noisy, we can only run in the low p regime anyway. And so this trade-off is actually advantageous because sure, the number of qubits in your intersecting light cone is growing exponentially with p, but we're only interested in the low p regime anyway, because that's the only one we can deal with. So this is actually a reasonable trade-off we are willing to take to access much larger problem sizes than qubits available. Here's what we do. We want to run on hardware. So we have like superconducting platform, 84 qubits, tunable couplers, some square lattice topology. And we have many subcircuits that we want to run, right? One for each non-zero entry in our correlation matrix. And so we want to put as many of them as possible on all the qubits we have available, right? And then another thing that matters for optimization is that, well, the solver has to be fast. So that's one reason we want to execute as many of them in parallel as possible. But then we know that like the building block we are running is the QAOA. That's a variational algorithm. Typically that requires finding optimal angles or parameters for getting good results. Well, because we are interested in 3 regular graph max cut, it turns out that near optimal QAOA angles are known. And so we will skip altogether variational optimization and just choose those. Here's the kind of results that we get. The results are just expectation values, the ICJ. So y-axis experimental data, x-axis the theory simulated. Experimental is not exactly what you get theoretically, well, because you have noise on hardware. A nice thing you can see here, maybe, or like a property that I want to highlight, is that kind of all the data points fall along the same line. And what that means is that between theory and experiments, your experimental expectation values are rescaled by some factor. But because they all fall along the same line roughly, that factor is constant. Because when we plug all of our expectation values together in our correlation matrix, we do an eigendecomposition after. Whether we do an eigendecomposition on a matrix or a matrix rescaled by some constant, that doesn't matter for the eigenvector. So it's actually like gives some kind of like sense for noise robustness for the algorithm. So good, we have the algorithm, the problem, we know how we're gonna run that. And so I'm gonna show now some results running on Rigetti's hardware. Y-axis is the performance, that's how close we are to the optimal solution. 100% is that we found the optimal solution. And the x-axis, it's like different number of variables. And for each of these sizes, we have solved 1,000 instances. So we have lots of statistics. For problems up to 256 variables, we solve a finite fraction of the problem optimally. And then beyond that, well, we are at about 99% approximation ratio. So we find solutions which are on average at 99% of the optimal one. I mean, we can run it classically. We have algorithm, and the longer you run them, yeah, exactly, the more likely they are to find the optimal solution. We just hope that like it is. If you run it multiple times and it always finds the same solution, it's exactly. So you know, in practice, what we do is like nothing more than the QAOA, right? And so we can compare what is the performance of the QAOA and what is the performance of what we do where the building block is just the QAOA. And so you run the QAOA and then this quantum relax and run where you don't do the greedy revisit, you get a time 10 performance improvement. And then if you do this greedy revisit by flipping the low magnitude entries of your leading eigenvector, you get an extra ×3 improvement. And so ×30 improvement in performance here with just the same quantum resources if you want. So those are experimental results at p equal 1. At p equal 1, we just need 7 qubits. At p equal 2, you need 19 qubits. And so we can not run it on hardware, but we can do the simulations. And so properties that we didn't touch on, but also quantum relax and run algorithm is that the performance increases monotonically with p. And at p equal infinity, it will converge to the optimal solution. So we have a good algorithm, right? 99% of the optimal solution. So maybe it makes sense to like try to benchmark it against a state-of-the-art classical solver. And so that's like what I'm going to explain here is how do we do that? So the quantum algorithm, it gets you to 99% on average. And so now we ask like, how long does it take for a classical algorithm to get there? Classical algorithm, if you give them enough time, they'll get there, right? But now we want to know who gets there faster, the quantum algorithm or the classical algorithm. And so the classical algorithm we're going to consider is a randomized algorithm. What does that mean is that every time you run it, well, you're going to get a different solution. And so there'll be an optimal time to run it. And how do we, I'm taking an example to make that maybe a bit more clear. And I'm doing that with simulated annealing. for 200,000 variable, just one specific problem instance here. The x-axis is the number of sweeps, and that's directly proportional to the runtime of your simulated annealing algorithm. On the y-axis, it's the time to match the quality of the solution returned by the quantum solver. If the number of sweeps is very large, well, the probability of finding the optimal solution is also very large, but you've maybe overshot it, right? Because the runtime is also quite long. On the other limit, if the runtime is extremely small, the probability of finding a solution matching that of the quantum solver is also going to be very small too. And so that's why the runtime goes up. And so there is a sweet spot. And for each of the problem instances, 1,000 for each of the size, we're going to find that sweet spot. And that's what we call the optimal time for the classical solver to match the performance of the quantum one. So here's like our optimal time. We're going to, and exactly what I just said. And we're going to consider 3 solvers: simulated annealing, general purpose solver, Borer-Montero. That's a well less known solver, but that's actually the best heuristic for the 3 regular graph max cut. And then we're going to consider a commercial solver, Gurobi. So here's some data: x-axis number of variables, the y-axis it's like the runtime, the optimal runtime for the classical solver, divided by the runtime of the quantum solver. If you're above 1, it means that your quantum solver is faster. If you're below 1, it means that your quantum solver is slower. And here we say, oh, we have 100 qubits, and that matters for how many subcircuits we can put in parallel on the chip. Now you're going to ask me, well, what do you put in the runtime of your quantum solver? Because it matters a lot. So here's what we have. It takes into account executing the subcircuit in parallel on m qubit, here 100. It takes into account the circuit compilation on a chain with worst case depth swap network. For putting the QA away, it's compiled with iSwap gates because that's what we have natively. It includes the measurements, 5,000 shots, the network latency because we communicate with a classical computer and the quantum one. Also, we need to reset the qubits after each measurement, so all of that is taken into account. And then you have all the classical steps, which are, well, we receive bit strings, we need to compute correlations. There is also the eigen decomposition of our correlation matrix, and all of that is taken into account in the T quantum. We can repeat the same with like 1,000 qubit because this is just changing the number of subcircuits we can plug in parallel, but it doesn't really change the conclusion. It just like kind of shift everything vertically. The conclusion here is that while we beat the commercial solver Gurobi for the large problem sizes, but we are very short of beating the state-of-the-art simulated annealing and Borer-Montero. So it's great, but not perfect. So how do we get to beating those two? And here I'm just going to show classical data. And that classical data is the solution accuracy versus the runtime of these 2 classical solvers. And that's going to give us like targets that we need to beat if we want to get a quantum advantage. And here's a window. All of these data points, like they surprisingly all fall on a line. And so this defines really 2 windows on that plot, where like if you get any data point in terms of runtime, you get that accuracy, which is like in the upper left corner, while you get your quantum advantage. Where are we? Well, that's where we are in that talk. So we are not there at all. And how could we get there? Well, with the quantum relaxant 1 solvers that we have, an option is increase P, the depth of your QA-away circuit. It's a bit hard to evaluate like how good this is gonna get with P because we cannot really run it. So instead of considering the y-axis solution accuracy, which is hard to evaluate versus P, something we can evaluate a bit more easily is the runtime with P, because this is just based on the number of gates that we run and so on, right? And so you have some model for that. So you have the model at p equal 1, p equal 2, p equal 3. And well, if you look a bit more closely on the x-axis, you will see that from p equal 1 to 2 to 3, it kind of like grows exponentially. You get like about an order of magnitude in runtime every time you increase p by 1. And we understand that, right? Because we are using our like light cone decomposition, and the subcircuit size, well, it increases exponentially with P. And the size of our quantum computer, it's fixed. And so you need to like put in there as many subcircuits as possible, but the size of the subcircuit increases exponentially, but the size of the quantum computer is fixed. So that's why you get an exponential runtime with P. Of course, that's just a runtime. It doesn't say anything about the performance. And so, you know, maybe the performance is going to like asymptotically get to like the optimal solution exponentially with P. And so maybe that would be advantageous. And you have some papers on small scale experiments that suggest that by the Harvard group in 2020. Then you can always say, well, you know, all of that is just classical data. Just find a better classical quantum hybrid algorithm that will get you to this quantum advantage window target. Then you can say, well, maybe the three regular graphs problem that you considered, they are just like too easy for classical solvers. And maybe the quantum solver is like, well, you know, maybe that's not the best problem. And so you can try other problem, but then, well, this problem maybe they are denser. You cannot use the light cone technique anymore. So how do you go to large problem sizes to actually benchmark that at scale that, well, you know, something may be interesting. And then, well, another thing we could think about is that we use the light cone technique because that's advantageous given the noisy hardware, but we don't have to. And if we imagine we had a big enough quantum computer to run like on 4,000 qubits, we wouldn't need to use our light cone technique. However, the sizes of the circuits would be so large that we probably would need to run in some kind of error correction regime, right? And when we talk about error correction, you have like more runtime that's introduced because you have overhead coming with error correction. And runtime matters for solving optimization problem. So then like, how does that like enter the game? Yep, and with all of that, some conclusion outlook, and I would like to thank you for listening to my talk.
Good question. Oh, actually, I was curious. So when you break this down, the smaller problems, how did P depend on the not the C here, the other P, the one when you break the smaller system sizes.
Yeah.
How did that scale with the system size?
Yeah, it's 1 plus 6, 2 to the P minus 1. So at P equal 1, it's 7 qubits at most. P equal 2, 19. P equal 3, 43. And then it goes to 94, I think, at P equal 4.
Is there a way to like, because the system is, I mean, it's small enough, I could just do also the part classically. Would that give you a new algorithm that's kind of inspired and be probably faster than the other ones?
No, because, faster, maybe.
Like,
yeah.
If you dequantize it and say, now I haven't inspired by this, but I'm...
Yeah, the only problem I guess you get with this quantum relaxed run solver is that the solution that you get, you cannot run the algorithm longer to get a better solution.
Okay.
Because that you would usually get that by increasing the value of P, right, in the quantum side. So you get a solution, but you know, is that actually enough in practice? Or I guess here it doesn't matter because those are regular graphs and that's not useful for any real world problem, but yeah.
The advantage is if you have sparse enough, but still big enough.
Yeah,
right?
maybe.
Yeah.
Thank you.
Thank you.